Hi guys, in the previous tutorial we looked at how to determine the moment of inertia of a rectangular shaped object about an axis that is passing through its centroid. So we looked at a question like this one where we're finding the moment of inertia about the y-axis, the y prime axis passing through the centroid the centroid. Then we also saw how to determine the moment of inertia about the x prime axis, again an axis passing through its centroid. Now, in this tutorial, we want to look at how to determine the moment of inertia of objects about an axis that is not passing through its centroid, but about an axis that is parallel to one axis passing through the centroid. Now, this is where the parallel axis theorem comes in. See, the concepts of determining, let's say you have the same rectangular object that we had in the previous case. Let's say you wanted to find the moment of inertia about this axis. You see, this axis is way off the centroid. What the parallel axis tells us is that if you know the moment of inertia about the centroid, which is this one, you can actually use this solution, the moment of inertia about the centroidal axis. We can use this to predict the moment of inertia about an axis that is parallel to this, provided we know the distance between the two axes. So if we know this distance, let's label this as a distance d, we can actually use it and the moment of inertia about the centroidal axis to calculate what the moment of inertia about this new axis is going to be. This is where the parallel axis theorem comes in. Now, why is it so helpful? Well, this is because in most cases, you will be provided with the moment of inertia about the centroidal axis. Therefore, if you already have the moment of inertia about the centroidal axis, it now just becomes a matter of you using the parallel axis theorem to determine the moment of inertia about any axis that can be given to you, provided it is parallel to the axis going through the centroid. So this is all that you have to get here. Now, how does it work? So let's say we have the moment of inertia about this axis. Let's say this is the x prime axis. So if we know the moment of inertia about the x prime axis like that, the parallel axis theorem now tells us that, see, the moment of inertia about this new axis, if we label this as the x-axis, so I can say the moment of inertia about the x-axis will be equal to the moment of inertia about the x prime axis, which is the centroidal axis, this axis there, but this has to be added to the product of the area of the whole thing, since this we're looking for moment of inertia of an area. So this is going to be the area of the whole structure, then multiplying the distance between them squared. So this is going to be the distance squared. This distance is the distance between the two parallel axes squared. So if the axis you were going for was perhaps a vertical axis, which is somewhere here, so for this part you would need the moment of inertia of an axis passing through the centroidal axis but parallel to this red one, which would have to be the vertical axis, this one here. Now for this part, you'd need, this is going to be the moment of inertia about the y prime axis, then the distance between them. So the distance between them would have to be this distance here. So this is what the parallel axis theorem works, or this is how it works. This is what it is. Now consider these cases. Consider this case here, this question. In this question, they are asking us to determine the moment of inertia for the rectangular area shown with respect to the x-axis. So the x-axis is way at the bottom here. Yeah. Now, according to the parallel axis theorem, of course, we see that here the parallel axis theorem would work because we already know the moment of inertia about the x prime axis. Now, the axis they want us to evaluate the moment of inertia about, it's an axis parallel to the x-axis. So, and the moment of inertia about the x prime axis was determined earlier. This is what we found. So using the parallel axis theorem, we are told to say that the moment of inertia about the x-axis now will be equal to the moment of inertia about the x prime axis, but added with the area of the whole structure of the whole rectangle multiplied by the distance between the two axes squared. So the distance between the two axes in this case is going to be a distance that is between the two. It has to be perpendicular to each axis. So this is going to be this distance between them like this. So that is going to be the distance I've labeled as D there. So this is how the parallel axis is going to work. Now, do we have what we need? Yes, we do. The moment of inertia about the x prime axis was calculated in the previous video. What did we find? We found that about the x prime axis, we had BH, this was cubic, and then this was over 12. Plus, how do we calculate the area of a rectangle? Well, the height, this is h over 2 of plus, then the other one is h over 2, so it's just h over 2 plus h over 2. So the full height here is just h. How about the full base? It's b over 2 plus b over 2, which is just b. So it's just base times height. So the area is going to be base times height there. This is giving us this. The distance between them. Well, the distance perpendicular to both axes, the x prime and the x-axis. So here I'm saying it's the distance between the x-axis and the x prime axis, perpendicular to both axes. In this case, that distance, I labeled it as d, but observe that that distance is just h over 2. That's the distance between the two axes. But that distance has to be squared. So what we have is h over 2, but now this has to be squared here. So that when we simplify this, we have bh cubic over 12 plus, this is going to be bh, and then this is going to be, when I square both the h and the 2 there, I have h squared over 4. So that second term just reduces to become, this is going to be bh cubic over 4. Now we can find the lowest common denominator, and that will be the 12. And then this is going to be bh cubic plus, that is going to be 3 bh cubic. When we simplify this, this gives us 4 bh cubic over 12. And this becomes bh cubic over 3. So this becomes the moment of inertia I about the x-axis. See how useful the parallel axis theorem was. We did not have to calculate any new moment of inertia, since we already knew the moment of inertia about the centroidal axis. We can now do the same thing even for the moment of inertia about the y-axis, provided we know the moment of inertia about the y prime axis. Try it first before you see my next presentation. So in this case, we now want to determine the moment of inertia for the same rectangular shaped object that we saw earlier, for an area, of course, with respect to the y prime axis. So where is the y prime, not the y prime, the y axis? The y axis is this axis here. Now, like we saw, or using the parallel axis theorem, we need to know the moment of inertia of an axis parallel to the y-axis but passing through the centroidal axis, or through the centroid, and that would be this one here. So we need to know the moment of inertia about the y prime axis. Luckily for us, we did determine the moment of inertia about the y prime axis in the previous or earlier in this same video. So this was the moment of inertia, not in the same video. I think we did this in the previous video. You guys can look at that if you haven't. So this is the moment of inertia about the y prime axis. Now, what does the parallel axis theorem tell us? It tells us that the moment of inertia about the y-axis can be found by just adding to the moment of inertia of an axis parallel to the y-axis but passing through the centroid, which is the y prime axis, plus the area of the entire shape. In this case, this is a rectangle. Then multiplying the distance between the two parallel axes. So what is the distance between the two parallel axes? It's the distance from here to there. It has to be perpendicular to both axes. So this becomes our distance d. In this case, observe that that distance would be the same as the b over 2 indicated by these boundaries. So based on that, we can then calculate the moment of inertia about the y-axis by substituting about the y prime axis. We found this was hb cubic over 12, then plus, of course, yeah, this is d squared. So plus the area of the shape. This is still a rectangle, so we're still seeing BH. Again, the full base is B, H over B over 2 plus B over 2. The full height is H as well, H over 2 plus H over 2. But the distance between them squared, in this case, the distance between them is B over 2. So this is going to be B over 2. But we just have to square this one. So this becomes HB cubic over 12 plus, this is going to be BH. Then here we have B squared over 4, which is 2 squared there. So of course, this reduces to HB cubic over 12 plus this becomes HB cubic over 4. In a similar way, the common denominator will be 12. This ends up being HB cubic plus this will be 3 HB cubic. So that finally we end up with 4 HB cubic over 12, or this will just give us HB cubic over 3. So this becomes the moment of inertia about the y-axis. So this is how the parallel axis theorem works. Very handy method. Let's see more examples in the next tutorial as we dive in more and more into moment of inertia. Perhaps we might even see what the polar moment of inertia is. Now guys, hope you found this helpful. If you did, let me know in the comment section. Let me know also what else you might want me to present on. We'll see you guys in the next tutorial.